So in Sarah's talk, we just heard about the progress in understanding strontium copper borate from the experimental side, and my talk is going to be about the same subject and our progress from the numerical side. And the approach we are using is iPEPS. So that's a two-dimensional tensor network ansatz to represent 2D ground states directly in the thermodynamic limit. And in recent years, it has become a powerful approach to study 2D strongly correlated systems. And the Shastry-Sutherland model is a particularly nice example where iPEPS really helped to gain many new insights over the past few years. So in particular, it's a system where for many years there has been a mismatch between experiments and theory regarding the structure of magnetization plateaus that appear in the system in a finite magnetic field. And iPEPS was really useful in solving this discrepancy. So by doing iPEPS simulations, we found here surprising results, which were in the end in contradiction with the previous theoretical prediction, which, because it turned out that these were based on the wrong initial assumption, and this in the end helped us to gain a new understanding of the magnetization process in the system. And in the end, a consistent picture between experiment, theory, and simulations. Okay, so I'll tell you about this story in the first part of my talk. We also briefly heard about it in Sarah's talk. And then the main part of my talk is going to be about the chemically doped Shastry-Sutherland model. So our collaboration with Sarah, where our goal was to get an understanding of the new anomalies which appear in the system. In the very end, I will also tell you something about strontium copper borate under pressure, which is also an active field of research, as you just heard in Sarah. Now, but first of all, let me just give you a very brief introduction to iPEPS. So I guess most of you are familiar with the main idea of a tensor network ansatz. So the main idea is to represent the quantum mini-body state by a trace over a product of tensors. And the best known example is the matrix product state, so which consists of put tensors on a lattice, so one tensor the lattice side, depicted by these poles here, and the lines attached to these poles corresponds to the indices of these tensors. And the accuracy of the ansatz can be systematically controlled by the so-called bond dimension, D of the tensors, so that in the end controls the number of variation parameters in your ansatz. So this is an ansatz for 1D or quasi-1D systems. And now the natural generalization of this approach to 2D is called a PEPS, or projected independent pair space. Now, as in the MPS, we have exactly one tensor per lattice side, but now on a two-dimensional lattice, and each tensor is also connected here to its nearest neighbor. Now, there exists also a version of this for infinite lattices, so with which we can directly represent a wave function in the thermodynamic limit. And the advantage of this is that there's no finite size and boundary effects here. Now, if you have a wave function which is translation invariant, you can simply represent it by one tensor A here, which is repeated on your lattice. But often translational symmetries are broken, and in this case, we need to use a certain unit cell of tensors which is periodically repeated. And this unit cell has to match the structure of the ground state. Now, of course, in practice, we don't know the right unit cell in advance. So what we do in practice is to run simulations with different unit cell sizes, and they check which unit cell gives the lowest variational energy, which then corresponds to the ground state. And we will see that we can also actually go to very large unit cell sizes, which was important here for our studies of the Shastry-Sutherland model. Okay, so we'll not really go into the details how we can find the most optimal variation parameters, so to have the best approximation of the ground state, or also how we can evaluate this 2D tensor network. But if anyone is interested, I'm of course happy to give you more details later. Okay, so let's move now to the Shastry-Sutherland model and just briefly repeat the main ideas. So it's essentially a 2D Heisenberg model on a square lattice with some additional couplings shown by these dashed lines, or as we heard, it can also be seen as a lattice of coupled dimers, and it has this very nice realization in strontium copper borate, where the copper ions carry the spin 1/2. So the lattice we obtain here is the same as you can see here. Now, the first thing we did a few years ago was to look at the phase diagram of this model without a magnetic field. And so if you go to the J prime over J equals 0 limit, then you simply have a state of decoupled dimers, right? So it's the dimer phase. And this actually remains the exact ground state also over a finite range of these values. Then in the other limit, we just have a Heisenberg model. So we have an anti-ferromagnetic state. And then in between, as we heard in Sarah's talk, there have been several predictions for intermediate phases. And a few years back, together with Philippe, we were able to kind of show that this intermediate phase is a placket phase, right? So this is a non-magnetic phase, which breaks the translational symmetries and where strong bonds are formed around such plackets. Okay, and now from an experiment point of view, what has really been of interest for already 20 years is to look at this problem in a finite magnetic field, because as you've heard, there have been several magnetization plateaus found in this compound already 20 years ago, right? And from the theory side, the challenge has been to understand what sort of states are realized in this magnetization plateau. Now, already early on, people realized that this system has almost localized triplet excitations. So, right, so you can take the ground state and just promote one of these signals into a triplet. And then what can also easily show is that if you put two triplets next to each other, that they feel a repulsion, at least on the near field level. And this has then led to the common belief that the magnetization plateaus that you have here corresponds to crystals of these triplet excitations. And so here you see some early suggestions of these triplet crystals. Right? So where in red you have the triplets and in black these are the singlets. Now this was back in 2000, and after that there have been many more experiments where people found new plateaus, for example at 2/15 or even higher at 1/4, 1/3, and 1/2. And in theory, people try to match this experimental sequence. However, even after many years, there has still been a mismatch between experiments and theory. So, for example, a plateau at 1/8 was found in experiments, but not in theory. And then it was never really clear why should there be a plateau appearing at 2/15. So this has been a puzzle for many years. And then it seemed to be an ideal problem for iPEPS, because with iPEPS, we can simulate all these magnetic structures in large unit cells. So the goal was to try to reproduce all these triplet crystals, check their variational energy, and then see what the resulting magnetization curve is. But then we really got a big surprise here, because it really turned out that this very initial assumption that these plateaus correspond to crystals of triplets was actually wrong. Okay, so what we found here is the following. So what you see here is one triplet excitation in this cell here. So the triplet has been formed on this dimer here. And then you also see a response from the neighboring sites. And these bonds here just mean that the energy between these bonds is particularly low. Right, so this is one triplet excitation, and here would be the spin structure of two triplet excitations that we obtained for a small bond dimension. Now with the small bond dimension, we can reproduce the mean field result, and that's what you see here. So we just have two triplets with repel each other, but it turned out that this is actually not the right solution. Namely, if you go to larger bond dimensions, then what we obtain is this spin structure here, which is a bit reminiscent of a pinwheel. And what this is a bounce state of two triplets. Okay, so it turns out that if you include higher order quantum fluctuations, that two triplets actually like to form these bounce states. And it's in the end these type of objects which form the crystals. Let me just show you here one example for the 1/8 plateau. So here you see the energy per side as a function of 1 over the bond dimension. So you see here how the variational energy is improved as we increase D. And now the two upper curves are the energy of a triplet crystal, and the two lower curves are the energies of the two different bounce state crystals. An example shown here. And as you see, as we go to larger and larger bond dimension, we clearly see a separation in energy, really showing that the bounce state crystals are favored. Okay, we found very similar results also for the other plateaus. below the 1/4 plateau. So in particular, this 2/15 plateau now suddenly made perfectly sense because it's really a regular structure of these, in terms of these bound state objects. Okay, so we then computed the energy of all these bound state crystals. Right? So there were many states that we had to consider here, and eventually then we computed the resulting magnetization curve. And what we found here was a sequence of plateaus which was in agreement with experiments, except the plateau at 1/5, which is not observed in experiments, but then we check what happens if we add a small but realistic Dzieloszynski-Maria interaction. And in this case, we found that this plateau here actually vanishes, whereas the other ones remain, so that in the end we obtained a sequence which is really agreement with experiments, and the end, which in the end really helped us then to get a new understanding of the magnetization process in this compound. Right? And based on these results, then it was also possible to reproduce them also with other methods. Okay, so let me also mention briefly another work on strontium copper borate in ultra-high magnetic fields up to 118 Tesla. So that was a joint work with several experimental and other theory groups. And what we did here was to do a direct fit also of the magnetization curve from numerics with the experimental data, where we then also determined the coupling ratio to be 0.63. What we also found in this work is the appearance of super solid phases. So that's an example of this 1/3 super solid, which we found on top of this 1/3 plateau. Okay, so I will not go into the details of these calculations, but in the end, it's, I think, also another nice example of a successful collaboration between theory and between numerics and experiments. So let me now come to the main part of my talk, which is about the magnesium doped system, so our joint work with Sarah. And as we heard in her talk, there are new anomalies appearing here below the 1/8 plateau, here denoted by HC1 to HC3. And there's even here, if you zoom in, another anomaly at even lower. Right? And from the iPEPS side, our goal was to get an understanding what the nature of these new anomalies are. Now, if you dope the system with magnesium, this induces non-magnetic impurity sites. So the way we model this is simply remove some of the sites from the lattice. So here these impurity sites which do not couple at all with any of the neighbors. And since this breaks up one of the dimers, we also have then a free spin on half degree of freedom next to such an impurity site. And now for an isolated impurity, this free spin will immediately align with an arbitrary external field. And the question is now, how do the presence of these impurities and this free spin on halves affect the magnetization process in the system? Now, the first key question we asked here is whether bound states actually get attracted or repelled by these impurity sites. And here I show you results that have been obtained in a 8x8 cell. So with one single impurity and one single bound state. And this is the lowest energy state. So you can see here that the bound state has been formed far away from the impurity site. So showing that there's effectively a repulsion between the impurity and the bound state. Okay, so that's the first key insight. And then the second question is, how does the lattice get filled in the presence of many impurities? Right, so here we considered a unit cell with 288 sites. And again, that's the unit cell, which is then embedded in our infinite system with a finite concentration of impurities, so just a random configuration. And then what you see here is the resulting magnetization curve of this system. And so the black line here is just the guide to the eye. So let us now go through this magnetization curve step by step. So right now we are at this field here, so shown by the red arrow. So here already all the spins, the neighboring impurity, are already aligned with the external magnetic field. And now if we increase the field further here, at this characteristic field HC2, we have the first bound state which appears in the lattice. And as you can see, it is formed as far away as possible from the neighboring impurity sites, right? Which is consistent with our previous observation that bound states get effectively repelled by the impurity sites. Now, in an infinite system, we can expect that there are many locations in the lattice with a similar energy to form a bound state, so that we can expect that the magnetization will jump at this characteristic field here, which is compatible with the anomaly that has been observed in experiments at the fields here, which are compatible with the value we find here. Now let's move on. So if we increase the magnetic field further, we have now a second bound state, which appears here. And then at another characteristic field, here HC3, we see suddenly also an appearance of a triplet excitation. Now, why is a triplet formed here instead of a bound state? The reason is that these triplet excitations are smaller in size than a bound state. So depending on the local environment of impurities, it can be energetically favored to put a triplet instead of a bound state excitation. And what we also observe here at this characteristic field is that there's a change of slope in the magnetization curve, which in the end we believe is the reason for the additional anomaly found in experiments at fields which are close to the value they have found. Okay, so from here we can increase the field further, and then the lattice just gets filled with these states more and more. Okay, so we got an understanding for these two new anomalies here. But now again, there's also additional anomalies at even lower fields. So the question is now, what do these correspond to? Now, earlier we saw that if we take an isolated impurity, that this extra spin here gets immediately aligned with an arbitrary small field. However, this is only true if we take an isolated impurity, and if we take now several impurities, then the interactions between impurities become important, right? So for example, if we take two impurities next to each other, then the free spin on half here will simply couple to a singlet here, so forming a low energy bond between the dimers, and it will take a finite energy to break up this dimer, right? So this is only going to happen beyond a certain critical value of the field, and we computed this critical value for this case here and found that this happens around 12 Tesla, so that's a value well below the HC2 we had before, right? So this is value we have here is somewhat lower than the experimental value. However, the value here was obtained with an isolated pair of impurities. So if you now add additional impurities here, this value will actually shift to higher values approaching the experimental one. There's also more types of these two impurity configurations with a lower excitation energy. So here are just two examples shown here, which in the end we believe is the reason for the additional broad anomaly that has been found in experiments. Okay, and also here, these values here will change if we add more impurities around them. Okay, so let me just summarize this part of my talk. So using large unit cell iPEPS simulations, we got a qualitative or semi-quantitative understanding of the novel anomalies observed in magnesium strontium copper borate. The simulation suggests that these two lower anomalies can be explained in terms of these impurity pair configurations which get excited. HC2 can be associated with the appearance of the first localized bound state in the lattice, so which leads to a jump in the magnetization. And then finally, HC3 can be associated with the appearance of additional triplets in the lattice, which leads to a change in the slope of the magnetization curve. Okay, now on the quantitative level, there would be still room for improvement. So we could go to larger unit cell size or taking disorder averages and so on. But in the end, we believe that this will not really alter our picture we obtained here in a significant way. Okay, so let me move now to another recent work on strontium copper borate under pressure, which was also mentioned by Sarah. So as we heard, if we put the system under pressure, it's a natural way to change the ratio of J prime over J. and a way then to probe the phase diagram of the Shastry-Sutherland model. And as we heard, there's now several experiments which found evidence of a phase transition into a gapped phase at around 1.7 gigapascal. So that's compatible with a placket phase. However, the phase that has been suggested based on neutron scattering data is another type of placket phase, so this full placket phase, so which contains a dimer in the plackets. And that's in contrast to the placket phase we have here, where the plackets are formed without the dimers. So that's this we call the empty placket. Now, one possible reason why there's a discrepancy between the two is that the model which we need here is no longer the plain Shastry-Sutherland model, but a more complicated model. And to gain insights here, we have recently considered a deformed or distorted Shastry-Sutherland model. So with two different types of dimer couplings and two different types of interdimer couplings. And then we studied the competition between these empty placket phase and the full placket phase. So we computed phase diagrams across several cuts in this extended parameter space. So the calculations here were done by Skelter-Krone and Ido Nissi, so PhDs in my group. And we also additionally had results from a series expansion done by Caroline Gold. So to make the story very short, is that what we found is that already a small deformation of the lattice leads to this full placket phase, so in agreement with the neutron scattering data, which means in the end that we need to go beyond the simple Shastry-Sutherland model and look at the slightly deformed model. However, right now, the exact nature and the exact coupling of this deformed model are still unclear, and further work is needed here to get a more quantitative understanding. Okay, now let me very briefly mention also some other recent progress. So there has been some new methodological developments over the last few years for doing finite temperature simulations with iPEPS. And we recently applied these ideas also to the Shastry-Sutherland model. And here I just flashed a very few results for the specific heat. So for J prime over J equals 0.5, the sign problem in quantum Monte Carlo is weak, so we can directly compare. And here you see we obtain a nice agreement with quantum Monte Carlo. However, if you go to larger coupling, then there's a strong sign problem. So you see here the error bars actually blow up in Monte Carlo, but with iPEPS, we can still access the low temperature here in a controlled way. And then finally here, I just show you a comparison with the experimental data where we obtain a nice agreement at low temperature. Now at high temperatures, things start to deviate, but this is because the spin-phonon coupling terms become relevant here, which are not included in the model. So we did more comparisons also with other methods, so with exact analyzation and also with the thermal pure quantum states, which were obtained by our chairman here, and which were published in this paper. And we're also currently looking into the thermodynamic properties of the system at larger coupling ratios, so to get an understanding of the compound under pressure. You still have, okay. Okay, so that's ongoing work. So we try to get some more insights here for the compound under pressure and see if we can also then match the thermodynamic data with the experiments. Now, very briefly, let me also mention that there has been progress in studying excitations with iPEPS, so using a special excitation ansatz. So the idea is to start from a ground state represented by this iPEPS ground state wave function, and then build an ansatz for an excitation as a momentum superposition. So we change one of the tenses here. So this idea was developed in Frank Verstraete's group recently, and we also made some further developments here in the recent paper. And here I just show you some benchmark data for the 2D Heisenberg model for the dispersion here. Right, so I will not really go into the details, but in the end, we hope now to use this approach also to study the excitations in the empty and full placket phases to have a more direct comparison with the neutron scattering data for strontium copper borate under pressure. Okay, so with this, let me summarize. So I've showed you several examples how iPEPS help us to get new insights into the physics of strontium copper borate. It's not the end of the story, as we heard in Sarah's talk. There's still many open questions which we hope to be able to address in future. So regarding the thermodynamics under pressure, the nature of excitations, and then also the magnetization process as you move into the plateau phase. So it's a very challenging problem, but also a nice playground, a challenging playground for the merit. And so we hope to make progress here in the future. So let me acknowledge all my collaborators, so in particularly Frederick Mila, who was involved in all these works, and then also Sarah Ravifar for the nice collaboration we had, and then also my students, Skelter Kuhn and Indonesia, and all the rest of them. And then finally, I would like to thank you for your attention.
Thank you very much. Questions?
I have a question about excitation with the ansatz. So can you capture like complicated excitations or will there be like
No.
So I'm going to repeat the question. So, so the question is whether you can capture complicated excitations and not only magnons and skinflits with the iPEPS excitation ansatz.
Exactly. So single-mode approximation would be, if you actually put a local operator here on the side, right? So that's your field. And what you have here is your outer tensor. So this can carry correlations over a finite region. So in that sense, you can indeed capture. You can really go beyond a single-mode approximation in a systematic way. Yes.
So the question is about thermodynamics of iPEPS, how it works.
Exactly. So the main idea for ground state is to represent the wave function as a trace of a product of changes. And now you can do the same thing for a thermal density operator. So you decompose the thermal density operator again as a product of changes. And then for finite temperature, what you can do is then an imaginary time evolution, where you start from infinite temperature, so where you just have an identity matrix, and then imaginary time above that state to your target temperature. And then in the end of the day, so we can really recycle many of the approaches we use for ground states, also in imaginary time evolution, to do calculations at finite temperature in a very similar way. But so far, let's say there's not so many benchmarks yet, so it's still unclear how far we can push this. And for example, also for the 3D Hubbard model, it will be very interesting to see how it will compare and how far we can get.
So can you give us an impression how off this IRIM scale, like in the cell size and what bond dimension?
So it's linear in the cell size, and in the bond dimension, it's polynomial, but with a high power of about d to the power of 10. So this sounds bad, but in the end of the day, also the bond dimensions we need to reach is much smaller than in one dimension with matrix colored states, right? So here we're talking about bond dimensions of maybe 5 to 10 to 20, depending on the model.
Okay, well, there's no further questions. Let's thank Philippe again.